This meeting is being recorded.
The next section in Chapter 16 introduces us to a specific type of reaction called the Diels-Alder reactions. And these we'll find to be very useful. And here we see this specific reaction is referred to as a 4+2 cycloaddition because we have two different pi systems here, one of which has 4 atoms and the other has 2. So that's where the 4+2 cycloaddition name comes from. And you might notice that we have the arrows, the curved arrows showing the formations of 3 bonds and the breaking of 3 bonds simultaneously. And these arrows can be drawn clockwise or counterclockwise to represent the same movement. So let's take a look here at the transition state. And again, we can see the simultaneous formation and breaking of 3 bonds at the same time. And we have this cyclic electron in a loop system here as our transition state. So we know that that's common to these, the transition state of these Diels-Alder reactions. You can also notice here that these reactions are able to be thermodynamically controlled. We see that the Diels-Alder product is favored at both low to moderate temperatures, and the product stability would dominate. So that's why we have this more stable product shown over here on the right. Then again, at higher temperatures above 200 degrees Celsius, we see what's referred to as a retro-Diels-Alder reaction, where our compound actually breaks down into the 2 starting materials that we see over here. And we will define each of these starting materials later on as the diene and the dienophile. So we see when we convert bonds or we break bonds and form new bonds, there is a value for Gibbs free energy associated with the enthalpy term in this equation here. So remember, bond enthalpy is a value that is given to a heterolytic bond cleavage. And what we see here is that we have those 3 pi bonds broken, and then in our product we would have 1 pi bond formed and 2 sigma bonds formed. So there will be an unequal amount of energy in the lost and gained bond formation. So we should see a negative change in enthalpy overall in this type of reaction, in these Diels-Alder reactions. So the enthalpy term would be negative, and then we should also see a negative entropy term because we're going to have a decrease in the entropy or disorder in our system because we have 2 products, two reactants that turn into 1 product. So our entropy is going down, so our change overall should be negative. So now that we've discussed these 2 terms, if we see a negative enthalpy term and this competing entropy term here, we should note that the enthalpy term must be larger than the entropy term for the reaction to be forward favored. Therefore, we would have again, if you recall, a negative delta G value, and we know that a negative Gibbs free energy is interpreted as a spontaneous reaction in the forward direction. But we see at very high temperatures, above 200 degrees Celsius specifically, the opposite reaction is favored, and the formation of the retro Diels-Alder products would be favored at this higher temperature. So again, the ideal conditions for Diels-Alder reaction would be at either room to up to about 200 degrees Celsius. So let's define the 2 reactants in our Diels-Alder reactions. We have our diene, which you can note, we have 1, 2 double bonds here. So since we have these 2 pi bonds, that's our diene. And then our dienophile, as the name notes, likes a diene, so wants to react with a diene. We should note down here that our dienophile, to be effective, needs to possess an electron withdrawing group, and we'll see on the next slide what some examples of those are. Um, or it would require such a high temperature, a retro Diels-Alder reaction will be favored. So we would have a fairly low product yield at a higher temperature if we tried to perform this reaction without an electron withdrawing group. So again, some of those electron withdrawing groups, commonly you'll see me abbreviate EWGs, can be things like this ketone group, an ester functional group, carboxylic acid, or a cyano attached to our pi bond. So our dienophile can take any of these forms shown below to be effective. So we'll continue with a second video on this section, 16.7, next time.